Alright, so we talked about count sort in class, which is a way around the fact that we didn't seem to be able to beat that n log n barrier for comparison-based sort. But count sort doesn't compare things. It counts things. So there's no comparisons that are going on. We make an array whose index is the number that we're considering, and we simply count how many copies of that number we have. And what we can do then is loop through that array of counts, which we know we'll get things back in order because the bins in that array come in order. And so this totally works. And we saw that in class. Problem is the time complexity and space complexity. Okay, well the time complexity of count sort is big O of m plus n for a maximum digit of m and n numbers. So this is fine if we have a bunch of numbers that are really small and they're all integers. But if we have large numbers, then this isn't going to work very well. So for example, if we have the numbers, a billion, 2, 5, and 6 trillion, it's not going to work very well. Because in this example, there are only 4 numbers. So even if I did something like bubble sort, it wouldn't take that long. But our m is huge. Our m is actually 6 trillion. We have to have 6 trillion bins to accommodate this. So we talked about a couple solutions in class. One of them is to actually, okay, so some people are like, well, let's maybe use a dictionary to store things so we don't have to store the bins that don't use anything. What makes that a little tricky is that we need to make sure that we can get bins out in the right order. The reason that I was able to sort these things in the end is because I could go through this array of counts and I would ensure that the bin that I started at, like bin 0 would hold how many zeros I have. Then I would move on to bin 1. Well, all the zeros are before 1, all the 1s are before 2, all the 2s are before 3. So because this array is indexed in order, I was able to do that. Problem with the dictionary is I would need to be able to loop through those elements in order too. And it's sort of like a chicken and egg problem. It's like, okay, well, I need you to sort the bins in the dictionary, but I'm trying to solve a sorting problem. So that's a little bit tricky and a little bit circular. What we can do instead of trying to cut down on the bins using a dictionary, what we can do is say, well, I'm going to fix the number of bins another way. And this is what brings us about Radix sort. What we're going to do is use a stability idea of sorting. So this is jumping back to the class exercise. What I could do is sort the numbers first in ascending order of the ones place. And if I have a stable sort, and I then sort them by the tens place, well, they'll also be sorted still by the ones place within ties. So for example, all the tens place that have a 0, I can see that those are in ascending order of the ones place as well. So 0, 4, 5, 7. 9, actually, there's an implicit 0 in the tens place here. So yeah, sort by the ones place first, then sort by the tens place, then sort by the hundreds place. And as long as this is stable, the final sort, however many places you have to go, will be the final total order. Okay. So now we only need 10 bins because every sort we're doing is only between 9 unique digits, or sorry, between 10 unique digits, 0 through 9. So we only need 10 bins. So that makes this a lot easier. We just have to repeat this count sort as many times as there are places, but that's not too bad because every time we go up a place, we accommodate another whole factor of numbers. So we can accommodate an exponential number of numbers for a certain amount of places. So we shouldn't need to go through too many bins, although we'll make this precise. Okay, so let's just do it. So I already set up the loop here. I said, first I'm just going to figure out, well, how many places do I need to go through? And that's just counting the max out of over all the digits. So now what I'll do is go through each place, so starting in the ones place and then going to the tens place and the hundreds place. I made a helper method that extracts the digits in the different place. So the convention is that 0 means get the ones place, 1 means get the tens place, 2 is the hundreds, etc. So it's how many digits you are from the right, starting at 0. Just so I can make it easy in the loop here. So place goes from 0 up to digits minus 1, and that goes through all the digits. Okay, fine. So we're just going to perform count sort, but we're going to do so just based on the current digit that we're at. So I'll loop through every element. So I'll say for x in array, counts at index. So I have to say get base 10 x and then the place that I'm in plus equals 1. All right, now here's where things get a little bit tricky compared to count sort. So let's say that I had just sorted this array by the ones place, and now I'm doing this sort on the tens place. So if I go through, I say, okay, here's a 7, I'm going to add 1 to 7. Here's a 0, I'm going to add 1 to 0. Here's a 9, I'm going to add 1 to 9. So I'm just looking at the tens place. Here's another 7. Here's a 6. Here's a 2. Here's an 8. Here's a 5. See what I'm doing? I'm just adding each time. Here's another 0. Here's a 1. Where was I? Just lost my place. Here is a 3. There's another 0. Here's a 9. Here's another 0. This is a bunch of zeros in this example. In the tens place. Here's another 7. Here's another 5. Here's another 2. Almost there. Here's another 5. There's a 0 here implicitly. If just a 9 in the ones place means 0 in the tens place. Finally, there's a 9 at the end here. Okay, that did it. And I think I strained my eyes a little bit. Okay, but when we take these out, you know, if we were doing what we did in count sort, I would read this. I would say, okay, 0, 0, 0, 0, 1, 2, 2, 3, no 4s, 3 5s, 6, 3 7s, 8, 3 9s. And that's certainly correct if I were just extracting the digit in the tens place. But somehow I lost all the information. Like all these zeros, well, that's a 70, a 600. What else has a 0? 804, 705, 707. I lost all those other digits. So that's not good. I can't just go through this and extract the whole sorted list like this. If I want to sort by the tens place, I have to remember the entire numbers. So what I really want to know is, okay, I'm going to copy, I've created this staging area. I'm going to copy things from the counts array into the staging area and then back. So I'm going to copy them out in the order prescribed here. But that's not the order that are going to come out in counts originally. They're going to come out in this order. So what I need to do is figure out, okay, well, sort of where do the ones in the tens place start? Where do the 2s in the tens place start? Where do the 3s in the tens place start? The 5s, etc. So what I'm going to do is create this cumulative sum array. Let me just write out the example first. So the zeros start at 0. The ones start at, so 0, 1, 2, 3, 4, 5. Okay, so if I have a 1 in the tens place, that's going to start at 5. The 2s, they start at 6. The 3s, they start at 8. So I jump 2. The 5s, actually, so the 4s, nothing. So they technically also start at 8, but, or I guess, sorry, no, they start at 9. But then the 5s also start at 9. There were no 4s. Okay, 6s start at 12, if I count it right. And so you get the picture. So I have to compute this information because that will tell me where to start putting each one of these digits. So I'm going to make an array. I'll call it csum, stands for cumulative sum. And first I'll just make it 0 for everything. But what I'm going to do is I'll say for c or I guess I'll say for I in range 1 up to 10. And I'll say csum at index I is equal to csum at index I minus 1 plus I guess I'll say the counts at index I minus 1. Okay. So what that's going to do is, so I start off at 0, but I skip that. Okay. If I'm trying to fill in the cumulative sum at 1, I look and say, well, what was the cumulative sum at 0? That's 0. Plus the counts at 0, that's 5. There were 5 zeros. Okay, so that's going to start me at index 5 for the ones in the tens place. Now I'm going to go up to 2. Okay, and I'm going to add on how many ones were there. And I'm going to start the 2s that amount past where the 1s started. Okay, so I make this cumulative sum array. Now what I need to do, and I'll leave this final step for you, is loop through the array. So loop through R, my array, and start copying elements, and start placing elements according to where the elements in their place start. Okay, so the first time I see a 3, I know that should start, I should copy that into index 8, but then increment that. Okay. Then increment that place. Okay. So the first time I copy in something with a 3, I put it in index 8. The next time I see something with a 3 in the tens place, I should copy that into index 9. And that will put them all in order. And then once I've done that, I can copy them back and then do the next round. Okay, so I'll have you finish that part.